Okay, so I am going to talk about chapter 6, and finally we are going to talk about chemical equilibrium. Probably that's the most sort of the important topic to summarize what you have learned from understanding the ideal versus real gas, learning different languages on entropy, enthalpy, Gibbs free energy, and so on, and then using that as a way to understand different types of behavior, phase transition, and what about the mixing itself, and how can I understand the solution, right? And so on is what we learned, and this is what we covered. But eventually, chemical equilibrium can be simple as this. A reacts, or the simplest one is A decomposing to B, and B can decompose back to A. This makes it the argument and mathematics much easier, so we're going to stick ourselves for that kind of a system. And the first topic is what we call 6A is, obviously, you remember in your general chemistry, equilibrium constant. And we call K. Remember the big capital K? And so that's the one. And probably equilibrium constant K is concentration A in equilibrium, concentration B in equilibrium. And this is what you know. And now for a given reaction, this is what people essentially let the reaction go. And then measure and on the equilibrium condition, what that means is you give a sufficient enough time for this one to go forward and backward, and they find their midway position at equilibrium and establish the equilibrium concentration and measure your K value. This is one of the characteristics to define a concentration of, if you want to call it, reactant versus product, and then how much can I make my products out of the reactant, and how can I manipulate this K to be favoring the more products or the reactant. So this is a practically more important, what you learn now is essentially can be applied to this. The first chapter is actually, the first section is just talking about equilibrium constant itself as a concept. And I think I briefly, last month, I briefly mentioned to you about this concept about equilibrium. So let's think about this diagram. Okay? And 0, and this is not 1, but what they call this. I'm using a different symbol. Okay? So this is a symbol. It's called psi, and this is the one that they use, and this is what is called the extent of reaction. In these cases, it's pretty easy, but in some complicated cases, this one is essentially sort of the reference 1 moles of entity that's changing from reactant to the products, and they're using the symbol in place of A or B and so on. So one notation that people do is, okay, change in the psi is, for as far as the A is concerned, the number of A mole. So it has a number of moles, but they are moving forward, and you are getting this one disappear. So it is in the reactant side, you are putting a negative sign, on the positive side. So in a conceptual way, this chi has although we are talking about back and forth, it has an implication of, let's say I'm moving 1 mole forward, and then that's the kind of implication of this notation we want to use. And so then this is specifically about that example, the psi. So this is a sort of the conceptual, what about if the reaction moving forward, and what's going to happen? And if you finish your reaction, and this is probably at the end of the Gibbs free energy, and the one thing that you will you will see so this is this is also a conceptual idea that as the reaction goes, this one lower the Gibbs free energy of the system when A goes to B and B goes to A, and this motion means A goes to B, and they are losing it. So this each moment, the slope is negative. Slope is negative. So this is a spontaneous reaction. And then when you reach this, and you have, if you want to move the forward, this is a positive delta G. So therefore, you are not going to do the reaction, and the system will resting in this position, at this calm position, at the extent of reaction like this. So this is what is called the system is at equilibrium. And to get more explicit information, delta G for the reaction, I guess is if you somehow know the Gibbs free energy of the system at different progression of the reaction, and then do the derivative with the extent of reaction, and under constant pressures and temperatures are all kind of regulated, and this is a 1, and obviously we knowing that this is a condition, the change is spontaneous. And what that means is when this is 0, this is at equilibrium. Okay? So system is at equilibrium when this change is no more. So you can think about this is a landscape of dropping the ball. They kind of go down, trying to find the minimum position as much as they can. Okay? So this is where they're resting in this place. If you're here, if your system starts here, they go backward to find the equilibrium conditions. So no matter where you start, they will end up being here as an equilibrium composition or equilibrium extent of reaction, and mathematically this can be expressed this way. And what else can I do? Okay. Also, you can also say, I guess so this is also true. This is another equation that showed in the textbook. You have the chemical potential B minus chemical potential A. That's the differences for delta G at any position. And there's this equation is also actually very conceptual and then misleadingly simple. But this equation is actually very complicated, because if you're looking at mu B, mu A, which is a chemical potential of A and B, when there is an A and B reaction going on, this is in the mixtures, right? So this is a composition dependent, so this is not a simple number. So don't look this one as like A minus B as a number. This is actually complex functions, minus complex function. So this whole thing is actually depending on the composition or extent of reaction, and we are looking for the way when this essentially this position delta RG is 0. This is the position that we are trying to find out. This is a mu A, mu B is a composition. But still, I'm very in a sort of a conceptual stage, and then I am going to getting some form of an equation that looks like is useful, and then the dealing with the gases gives a much more simpler form that we can define the delta GR. So Okay, so this is a equilibrium constant number one. And then now the actual case of for the perfect gas. Let's really get the what is an equation that this one looks like. And this one is essentially difference between products and your reactant. And this is a molar Gibbs free energy. So this is UB plus RT natural log, and then P naught PB minus UA naught plus RT. So this is what we learned before. Each one, in terms of chemical potential, their partial pressure divided by the standard pressure, which is a 1 bar. This is just a generic format for the case when we are dealing with this case. And in particular, when we see the delta R means, we are kind of assuming the before and after scenario going forward, and that's my reference point. So what am I ended up having it is a mu B minus mu A. Okay, that's the term. And these two terms, they are going away, and I only got RT, ln, PA, PB. And then well, this one, I want to redefine this one as, I think I have a typo here. They're going to rename it, this one as delta R G at standard state. So all of a sudden this equation has something that probably you have seen before in general chemistry textbook. If they just talk about what they did is, so RT ln Q. So this is now the generic form. And the Q is what is called the reaction quotient. Which is essentially what that means is, I quote unquote, product ratio or product over reactant. Just think that you guys even deal with that in the general chemistry. And remember that we talked about the Q. So this is a general form. We just give you an actual example for pressure ratio as any kind of ratio represented by Q, which is a reactant in the bottom and the product in the top, and that's the generic form. And then we are going to combine this one to be 0, right, at equilibrium. So situation even gets even more simpler here, saying that okay, in the equilibrium this must be 0, and this Q becomes what we call decay. So then all of a sudden that this whole equation boils down to something very simple equation for us to handle. And this is the one that I think that I think that you typically only saw the final form in many introductory levels of Chem book. So this 0 is an equilibrium. This is the equilibrium. RT. Okay. So now you start to see this correlation between the delta G at standard state, delta G at for the reaction, and ln K, but there is this portion goes in. Okay. So what that means is, we can think about this way as ln k, which is essentially nothing but minus RT delta RG. This is the one kind of the important kind of correlation that we can get from the equilibrium constant and their Gibbs free energy divided by temperature, and so that's their correlation. So somebody wants to do, and at this stages they also want to put it in delta RG. Standard state is minus RT ln k. And this is the same form. Sometimes you're using this, sometimes you use the other one. Remember, what's important here is we do care about the k, but actual k natural log form is g delta g divided by temperature. Right? So this is their correlation. So ln k and the 1 over temperature times the delta G is the one that can be defined. We can essentially find out the equilibrium constant if you know how to calculate or estimate delta G for the reaction under standard condition. So this standard condition, once again, is that the pressure is 1 bar. The temperature is not designated, so you have to, temperature has to be specified temperature. They have to let us know what temperature they are looking at, so we can looking at the difference in these two. Okay. The final comment on this is, where do you get this form from? And I can give a very simple argument on doing this. So here's an equation that putting into a graph. So let's suppose that I'm looking at the G, and we are looking at A goes to B. Something has a higher Gibbs free energy, something has a lower Gibbs free energy. So I can definitely kind of put, something looks like that. This is I guess the extent of reaction from 0 to the reaction completion. So in here, you're starting with a pure A. And if you have